Okay, so now let's look at next chapter, so electron beam lithography. So far we have learned about optical lithography, EUV lithography, and X-ray lithography. So they all use a mask. So they use a mask to copy the pattern from the photo mask onto the resist. For the case of electron beam lithography, so we use a focused electron beam by direct writing. So that means we do not need any mask. So we create the pattern rather than copy the pattern from the mask onto the resist. But because we create the pattern pixel by pixel, it is a very slow process. So that's why electron beam lithography is mainly used for the research and not much for the production. So even though it is used for the production of the photo mask or mold for non-imprinted lithography. So why electron beam can be focused to very small feature sets? So one reason is because of the wavelength for the electron beam is much smaller than the wavelength for the light. For example, for the particle, so what is the wavelength? So what is the wavelength of a particle? Sorry. So if you know the energy of the electron, how do you calculate the wavelength? So lambda equal to how much? So this is given by the Broglie wavelength is given by h over p. So p is the momentum. So h is the Planck constant equal to h over mv. If you know the energy, energy is given by 1 over 2 mv squared. So mv equal to 2 me equal to 2m energy. If we use the electron volt as energy, so in that you get a formula like this. So lambda equal to 1.226 divided by square root of the V. So V is the electron volt. For example, when V equal to 30 kilovolt, if this way is 30,000, then you get a number of 0.007 nanometer. So as you can see, the wavelength is much smaller than the wavelength for the light. So this is important reason that electron beam can be focused to very small spots. For the case of the light, so we have a similar formula here. For light, so we know the lambda. So for light, energy is given by HF. This is the energy for the photon, hc over lambda. So then lambda equal to hc over E, so equal to hc over E. If we use electron volt, it is given by hc over EV equal to 1.24 over V. So here, if we have 1 volt, so this one is nanometer, so this one is micrometer. You can see the electron beam give you much smaller wavelengths. We have seen that for the case of the PMA resist, so when we have the when it is exposed to the X-ray or it is exposed to the electron beam, the chain will become shorter molecular weight. But the energy to cut the chain, the chain is about 110 electron volt. The energy for the electron beam is 5 to 10 kilo electron volt to do the electron beam lithography. So we need this high energy in order to focus the electron beam to a small spot size and well to get large beam current. So we need this high energy even for the ICM. So normally we need more than 1 kilo electron volt. So you can see it's much bigger than the energy needed for the breaking the chemical bond. So as a result, the primary electron beam is not so important for breaking the chemical bond. It is the secondary or older electrons that are responsible for the bond breaking. Now, those energies, they have low energy. Those electrons, they have low energy, like a few tens of electron volts, so closer to the bond energy of the carbon-carbon bond. Now here is a brief history of the electron beam lithography. So the main work started in the 1960s. There was a breakthrough in 1968 when the polymer PLMA was discovered to offer very high resolution, very easy to work with. So this is a positive resist. So even for today, researchers in the world, they still use PLMA as the most popular resist. But this is not good for the production because, as we will see later on, this resist has low sensitivity compared to other resists. But if you just care about the high resolution and cheap and easy to work with, this is the best choice. There was faster growth in the 1990s when the nano began to become a hot topic. So more and more people start to do the electron beam lithography in the 1990s. So around year 2000, a focused ion beam come out. So we will see focused ion beam in next chapter. This will compete with the electron beam lithography. But even for today, EV lithography is still more popular than the focused ion beam, because focused ion beam is higher cost and slower speed. So roughly speaking, there are three types of the electron beam lithography system. So the first one is the ICM conversion. So you have ICM, it costs about $500,000 to buy ICM. They add about $100K to convert it to the EV lithography. So what do you need? You need a beam blanker and also need some hardware controller. Because normally for the ICM, we scan the beam. So we scan the beam from the top to the bottom. But when we do the electron beam lithography, so we need to control where the beam moves. The beam is here or the beam is here. You need to control where the beam to move to the exposure. So this is the hardware we need. It is also called a pattern generator. It's pattern generator. So MPGS is the company created by Nabiti. So Nabiti, this is a one-person company, but it was very popular. And even today, many people use MPGS system. It is the nano pattern generation system. So what is beam blanker? Because when we do the EV lithography, for example, we want to expose this point, and we want to expose this point. So from here to move here, we want the beam to be turned off. So to turn the beam off, it is the beam blanker. So in principle, you can use a shutter. You use a mechanical shutter to turn off the beam, but mechanical shutter is not efficient. So we use an electrical beam blanker. So what do we do? So you have a parallel plate. You apply a voltage here. You apply a voltage on the parallel plate. So electron beam come down. When the voltage is zero, so you put an aperture here. So when the voltage is turned off, you get electron pass through. So when the voltage is turned on, electron gets deflected. We have the here parallel plate. So because of the electrical field, electron gets deflected and blocked. But this way, it is blanket. It is blanket or blocked. But this is how the beam blanker works. Second one is the dedicated EV lithography system. This one is also based on ICM, but normally we have the interferometer stage and the focus correction to give you much better control over the electron beam positioning on the wafer, and also to maintain the focus. But this one costs about $1 million. For example, the RIS system belongs to this category. So this system is mainly used for the electron beam lithography, but you can also use it to do the ICM imaging purpose. So the third one is the EV writer. This one typically use 100 kilo electron volt energy. But this 100 keV does not give you any better performance, but we have the one that will not give you any higher resolution or higher sensitivity. Actually, it will give you lower sensitivity. But we have 100 keV, it's easier to give you higher current. You can get higher current, and also the beam can be better controlled. Because all the 100 keV system, so they have something called dynamic adjustment, or dynamic focus, or dynamic estimation. But what's the meaning for this? For example, if you do the exposure of the square, if you expose this square, so the electron beam comes from top. So you can imagine, at the center part, if the center part is well focused, if this is well focused, then at the corner part, the beam will not be well focused. And also, if the beam is you have well adjusted with low estimation, when the beam comes to the corner part, there may be estimation. So that means the beam may become, at the center part, the beam may be a tiny spot at the center part. At the corner part, the beam may be something like this, big and elongated. But because of the usage of the dynamic adjustment of the focus and estimation, so that means So when the beam comes to the different place of this square, the beam will be adjusted such that everywhere in this red field, the beam will be well focused and without astigmatation. So this is called dynamic focus or dynamic astigmation. So this way, you can write very large writing field, can be 1 millimeter writing field, and everywhere in this writing field, the pattern will be well designed. But this is a very useful feature because otherwise you have to use very small writing field. That is make the writing very slow. So this one is also, you can do it for a long time. It's very reproducible. You can do the exposure for days, but it also costs more money. So this one, the representative company to making the EV writer is the VSEC and the JO. So this is the Japanese company. So VSEC used to be a company, but now this about 2 or 3 years ago, VSEC was bought by RIS. So now this VSEC is part of RIS. So now we look at electron source. So electron source, for the electron source, so first we need a emitter. So this part will emit electron. Then we need extraction. This is extraction voltage. So the electron will be extracted. But this one is obviously should be a plus. So electron will be attracted. Then we have the lens. To focus the extracted electron. So how to emit electron? So we need to give some energy to emit electron. So what you can think is the thermal energy will heat up, or we have electrical field. In principle, you can also shine the light. When you shine the light, because of the photoelectric effect, the electron will also come out when you shine the light. But this one is not efficient. But in reality, we use either heat or electrical field to generate electrons. So as a result, there are 3 types of the electron guns. The first type is the thermal ionic emission gun. We use the heat. Why it is called thermal ionic? Because when the electron come out, it leaves behind an ion, right? When you lost the electron, it leaves behind an ion. So this is called thermal ionic. The second one is the field emission gun. This is electrical field. So we have the tunneling current. The third one is the combination of the thermal and electrical field, which is the Schottky gun. It is field assisted. So we have electrical field assisted thermal ionic emission. So whether it is field emission or not, I will think about this in a strict way. So this depends on whether tunneling is important or not. So we have very sharp tip, very sharp tip, which give you very high electrical field at the sharp tip. Then the tunneling will be important. Then we say this is a field emission. So otherwise, we shouldn't say it as a field emission. So now let's look at first a thermal ionic emission. So you can see we have a tungsten filament. Tungsten filament will heat up, we apply some voltage, the electron will come out. It's very simple. This one costs here. This is some years ago, $12. It lasts a few hundred of hours or 100 hours. So the idea is that in the electron, in this tungsten, we have this here is the energy level. So what is this energy level? So I think you know about this. But this is the Fermi level. So the energy difference between the Fermi level and the vacuum level, this one is called a work function. This is work function. For the electron to come out, it needs to overcome the work function and come out. Some electrons, the energy is given by 1/2 mv squared. This energy 1/2 mv squared. So the distribution of the electron, some of them will have very high voltage. This is the very high speed by chance. Then they have energy high enough so they can come out. But majority of them, still they will not come out. Because even though we use at 2,000 degrees, this will look like a high temperature, but the thermal energy is only 1.38. This is the Boltzmann constant times 2,273 Kelvin. This is the Celsius, this is Kelvin, divided by charge, which gives you 0.2 electron volt. So even at this high temperature, most of the electrons, they have energy 0.2 electron volt. much smaller than this work function. This one is typically a few, like 4 electron volt. So as a result, only tiny percentage of the electron, they have energy high enough that can come out. So the current that come out depends on the temperature and the work function. You can see the current depends on the temperature here and the work function. So here the work function, they use EA. EA is the same thing as the phi. It's the same as the phi. So here are the properties for the different materials. So tungsten is a good material because for the tungsten, the work function is not very low, but it is okay. But it has a very high melting temperature. So we can operate at a relatively high temperature to give you higher thermal emission. Another popular choice is this metal. It's called the Lab 6 La. So La is the element, lithium element. B is boron. So this is the Lab 6 filament. So this one can give, it is more expensive, 5 to 10 times more expensive than the tungsten. So this tungsten, this is really cheap. This is more expensive, but it is also longer lifetime, and it is brighter, have higher beam current density, but we need a higher vacuum because this material is reactive by the oxygen. So this is the thermal emission. So now let's look at tunneling. Tunneling is field emission. It's a field emission again. So to have the field emission has to be really sharp, so that we have very high electrical field at this apex. So we need it to be sharp to have high field. So the field needs to be higher than 10 to the power 8 volts per meter. Normally it can go to 10 to the power 10 volts per meter. So very high field. Because we have very high field, we need very high vacuum. Otherwise, there will be arc over. There will be electrical breakdown, because there may be some gas molecules that will be discharged, breaks down. So we have small beam size because the electron only come out from the apex. So the beam size is really small because only the apex contribute to the electron. So how to calculate the tunneling current? So when you, at your quantum mechanics course, and I know you'll learn something like this. You have, so this energy barrier here. So electron come here, and will tunnel through. So this is why you can solve it. But here, the energy barrier is this shape. So here is when you have very high field, this is the slope. So the slope of this line give you the field. It is a triangular shape. So the barrier is something like this, from here to here, a triangular shape. So this is why this triangular barrier is difficult to calculate, not as easy as this rectangular barrier. So this one was calculated by the project follower Nordheim, given by this formula. So you can see the first smaller barrier, higher current. So this makes sense. Smaller work function, higher current. Higher field also give you higher current. So this field emission gun tunneling current is dominant. The tunneling current dominates. But this is called a cold field emission. So why is it called cold field emission? Because this one operates at the room temperature. There is no need to heat up. So the current does not depend on temperature. So we do not need to heat up. Room temperature is good enough to have the tunneling current. So it is cold. But the problem at the room temperature, so even though with very high vacuum, there may be some contaminant in the chamber. So the gas molecules in the chamber, for example, some oil molecule in the chamber. But those oil molecules will come to the tip. So we have the insulating molecule come onto the tip. So the current will drop. So this will decrease the tunneling current and also cause high noise because the molecule, the monolayer build up, come in, come out randomly. So as a result, this one is not so good for the electron beam lithography because the current is not so stable. But still, you can use it. No problem. But the pattern design, the line edge roughness will be not as good as the Schottky emission, as we will see later on. But for the ICM imaging, this noise is not a problem, because for the ICM, for example, when we make an image like, we can have 1,000. We take an image, take about 1,000 by 1,000 pixel. This number of pixel. If this takes 1 second, this is very fast to take one image. For each pixel, you have 1 microsecond. Each pixel, you have 1 microsecond dwell time. Within this 1 microsecond, the noise will be averaged out. So this is not a problem for the ICM imaging. But when you do the lithography, the dwell time, that means the stay time, electron stay at this spot maybe for nanosecond, or maybe 0.01 microsecond, a very short time. Within this short time, the noise will be a problem for the lithography. For the imaging, this is not a problem because this is microsecond, so the noise will be averaged out. So now let's look at a third type. It is called a Schottky emission, Schottky emitter. So in this case, the first, it is a thermal emission. It is still thermal ionic emission. So electron still needs to come out. But the difference is that the barrier here is become lower. Electron can come here and come out. The barrier here is lowered by this amount, delta phi. So overall, it is still a thermal emission, but here the EA was replaced by the phi minus this term, phi minus this term. So this term is the delta phi term. So we can give an example. So for the case of the field equal to 10 to the power 8 volts per meter, so this is not so high, moderate electrical field, you can calculate this term to be 0.38. At this temperature, KT equals to 0.15 electron volt. Then the current ratio with this term or without this term, 0.38 divided by 0.5 equals to 13. That's why you get higher current when you have the lower barrier height. But how come you can lower the barrier height when you apply a field? How come the barrier height become lower? That means, so how come electron is easier to come out when you apply a very high field? So the physics is like this. So you have the tip. You have a tip. You apply a field. When you apply a field, there will be many negative charges. There will be many negative charges accumulated at the apex. If this particular electron, if this electron come out, it is actually pushed by those electrons. So those electrons here will help this particular electron to come out. That's why we have very high field and easier for the electron come out. This is because of those pushing force, because of the Coulomb repulsive forces. So here is the thermal emission, but normally people call this one as field emission gun. So because when you say field emission make it looks better, you can sell the equipment at a higher price. But actually, this is not truly field emission. So if you turn off the heat, there will be no emission. So the main source of energy is still the thermal energy. So the field is just to lower the barrier. Because we have both thermal energy and the electrical field, so the current you can get larger current. So this is good for the lithography because when you have larger current, you can reduce exposure time. And also because it is hot, it is always hot at 1750 Kelvin. It is always hot. There will be no contamination. All the contamination, when they come to the surface, it will be burned away. It will be clean. As a result, so the current will be very stable, much more stabler than the case of the cold field emission. Here there is the zirconium here. So at high temperature, the zirconium will be melted. When it got melted, it flows to the surface. So the surface is covered by a layer of the zirconium. But this material has lower work function. So this helps to make the emission easier because this material has smaller work function. So eventually, this one will be depleted. Then you need to change the tip. So to change the source costs about $10,000. So this is the Schottky emission. So now let's look at the size. So for the case of the thermal emission, so we know it's not sharp. So for the thermal emission, it's very blunt. But fortunately, even though even though this part is blind, even here is blind, because we have this extraction voltage and also focusing lens. So electron come in, they come out. So effectively, this part is the size of the electron beam, not this part. This is really big, but this part is small. So this is the case. This is called effective Euro source. This one with electron beam actually come to here. So this is the Euro source. For the case of the field emission, including cold field emission and the Schottky emission, so electron emission from here. So you can extend the line here. So effectively, electrons appears to come out from this spot. So this spot is called a virtual source. Because this one, electron they don't come here. This is not your focusing point. It's a virtual source. The same thing here. So when the electron all come out, you do the extension. This 3 nanometer here, this 3 nanometer here is the source that will be focused to the downstream to go to the wafer. This is 3 nanometer. So even though the tip itself may be 100 nanometer, but the size of this virtual source is about only 3 nanometer. So this table compared the different sources for the electron beam. So we just look at cold field emission. So we use tungsten, room temperature. It's very sharp. We need a very high field. So it is very sharp, 100 nanometer. So this one 1 micrometer. This one 60 micrometer. So this is really sharp. So the radius is only 2.5 nanometer. So here 3 nanometer here. It's very sharp. You have very small virtual source radius. Because it is all the currents come from this small spot. So the current density is very high. So we have 17,000 ampere per square centimeter current density. But the total emission current is not very high because the current only comes from this small spot. So this one, the current is not as high as the Schottky emission. It is brighter than other emission because it comes from the smaller spot. So the beam current can be 0.2 nanoampere, but actually, I know 10 years ago, Hitachi cold field emission SEM can go to 2 nanoampere. This one is the 10 nanoampere. So today, state-of-the-art EV lithography can go to 1,000 nanoampere. You can get much higher current. But we have much higher current, you do not have very high resolution. So the energy spread is 0.3 electron volt. That means, so we have, for example, 30 kilo electron volt. So this is the energy we want. It will be 30 plus minus 0.3. This is the energy spread. So for the cold field emission, we have very high noise because the contaminant molecule come to the surface randomly. And also we have high current drift because of the same reason. So the contaminant molecule, which is insulating, will build up on the tip surface to lower the current. To minimize the contamination molecule, we need very high vacuum and last about 2,000 hours. But this one we need flashing. So we need flashing, but other we do not need flashing. So in the flashing process, so the contaminant, so this is the tip. You have lots of contaminant on the surface. You have one monolayer of the contaminant on the surface. But during this flashing process, this contaminant will be burned away. So you get a sharp tip, clean sharp tip again in this process. So normally this flashing process was done every morning. Then the SEM will be good for during the daytime. So now let's look at electron optics. So here is the schematic of the electron optics. So we have the electron gun, condenser lens, beam blanker. So we have talked about beam blanker. This one is needed for the lithography, but not needed for the imaging purpose. We have the zoom lens, stigmation, aperture here, projection lens, and deflection. So normally we use electrostatic lens. We can use electrostatic lens. So the structure for this electrostatic lens is something like this. So this one is the grounded. This one also grounded. This one we have positive voltage. Like this, grounded, positive voltage. So this is the electrical field. So this is the potential for the same structure. So when the electron comes from the left, somehow it will be focused. So this is not obvious. So why we have this kind of field, electron will be focused. So this is why I said here. So electron optics is not obvious. It's not obvious. It's hard to imagine why it got focused this way. So we don't know why it is focused. It's not so clear why it is focused this way. So you can take another example. So you have a positive charge here. So you have a positive charge. So when the electron beam come here, when the electron come here, it will be bended. Another electron come here, it will also be bended. So it looks like this positive charge can effectively focus electron beam to a spot. But actually, this is not a very good focus, because if another electron comes from here, it will bend it here. So see, another one comes here. So this one, it will be focused to here. So you can see a single positive charge has the focusing power, can focus electron, but this is not well focused. It's not, you don't have a very well defined focal spot. And this is the electrostatic lens. So we can also use magnetic field to focus electron beam. So you can see, so when we have the uniform magnetic field, if the speed is like this, so you decompose the speed along this direction and also along this direction, the electron will move in the circles, then move to the right, like something like this. There's no focus. There will be no, it will not be focused. But we have the variable field. And somehow electron turn, and suddenly it got focused. So you can see electron come here and they got focused. Again, this is not obvious why it is focused, but by the good design, you can make it focused. For today's ICM and EV lithography, so actually we use magnetic lens. So we use magnetic lens. We do not use electrostatic lens, because when we have electrostatic lens, so we have very high electrical field. This high electrical field can cause electrical breakdown. So the area here has very high electrical field, then there may be electrical breakdown if there is some gas molecule in the chamber. But this is not good. So this part will be burned if you have the arc by the gas molecule in the chamber. Now we look at the factors that limit how small electron beam can be focused. This is the aberrations. So ideally, so with the lens, so electron come in, they will be focused to a geometrical spot. But in reality, there is aberration. Aberration is defined as the deviation from the ideal case. But there are, for example, here you have this mesh. When you have the lens, there is optical distortion or aberrations. So this is for the light. For the electron beam, you have similar thing. They get blurred, distorted, and those kind of aberrations. There are geometric aberrations that include spherical aberration, field curvature, estimation, and distortion. There is also non-geometric aberrations that is not related to the geometry, including chromatic aberration and diffraction. In the light optics, those aberrations can be eliminated because the single lens here actually is not like a single lens. For example, the lens in the camera is not just one lens. You can have many of them. You can put one here, another one maybe, another lens here. You put another one here. You put many of them together. And you can control the surface, you can control the shape of each of them. By the well-designed, this geometrical operation can be eliminated. It can have hundreds of lenses to have zero geometrical aberration. But in the electron optics, we cannot control the magnetic field or electrostatic field arbitrarily in the space. As a result, this aberration will stay. So the first one is the spherical aberration. So in this case, somehow electron along the closure near the axis. So near the axis is focused to here. Farther away from the axis is focused to here. So you can see they are not focused at the same spot. So this area here is called DOLC, disk of least confusion. So this area, So this area is the smallest part. This is smallest. So the diameter of this smallest part is given by this formula, 0.5 CF alpha cubic. The CF is related to the working distance. So normally, smaller working distance, that means the closer you put the sample to the lens, you get higher resolution. You get smaller aberration. So alpha is this alpha angle here. So you can see, depending on the alpha cubic, the very highly dependent. So in principle, you can make the alpha smaller. For example, if you put the aperture here, you put the aperture here. So this way you get smaller alpha angle when you put the aperture here. Electron only come from here to here. Then the alpha angle become this part. You get smaller aberration, spherical aberration. But the beam current also depends on the alpha angle by alpha square, because the beam current is proportional to the area of this aperture. The area of this aperture is proportional to the alpha square. So we cannot use too small alpha, because this will make the beam current very low. This will make the exposure time long. The next one is the chromatic aberration. This one is easy to understand. So you can imagine electron come out. So when you have lower energy, it's focused here. Higher energy is more difficult to focus here. So again, this part here is the small disk of least confusion. It's given by CC, this constant, alpha, this angle here, delta E over E0. So this delta E is the energy spread over the electrons. The current come, here's the number here. Energy spread and the gun exit. So this number here is the delta E. So for example, we have 30 keV, and it will be 30,000 plus minus 0.3. So this is the energy spread in this formula. Delta E is given back here. It's also delta V over V is the same thing. The third one is the diffraction. So this is the same idea as the light. For the light, we have diffraction, and we use the Rayleigh criteria to decide the resolution limit by the diffraction. So here we have the same formula, 0.61 lambda over NA. NA is sin alpha. When the alpha is very small, it's equal to alpha. So lambda, we know is very small. For example, 1 keV, 0.04 nanometer. But the alpha is also very, very small. So in the end, this term cannot be ignored, because the alpha is only like 10 milliradian. So 10 milliradian is very small. So how small it is? So 1 radian equals to how many degrees? So 1 radian equals how many degrees? So it's divided by pi times 180, should give you about 60. So 1 radian is about 60 degrees. So 1 milliradian will be 0.06 degrees. So it is very small angle here. So here the angle looks big, but actually the alpha here is well below 1 degree. Very, very small angle. So besides of those, so we also have the astigmation. So astigmation is because of the focal point along the x direction and the y direction is not the same. So in this example, along this x direction is focused here. Along the y direction is focused to here. So obviously, this way you don't have very good spot size. And the middle part you get circular shape, and near here you got elongated along this direction. Here you got elongated along another direction. From this, you got the minimum spot size given by C alpha, A alpha. It also depends on the angle. So you can see this is because the focal point of x and y is not the same. So what caused this asymmetric? Distortion? So this is because we use magnetic lens. So we have magnetic lens. There is the hysteresis. So what is hysteresis? If we draw the magnetization of the material, you remember it is something like this, rather than something like this. We have something like this, there is no hysteresis. We have something like this, we have the hysteresis. So because of the hysteresis, we have fixed the field, H field. We do not have this is the magnetization of the material. Magnetization of the material. So you can have different M for a certain H. How much M you have depends on the history of this magnet. So as a result, the magnetic field is not well predictable. As the length. So the X, Y, and may not be the same. Another source of the asymmetry is because of we have the apertures. There may be some contaminant, some dirt on the aperture. The dirt on the random place of aperture. This gives you another source of the asymmetry. So fortunately, we have this stigmation. This can be eliminated completely by using magnetic field. So you look at here. So this one is the stigmator. Here is the magnetic field. There are totally fog of them. So we have the stigmation. So you adjust those the fog magnet such that the stigmation can be compensated, can be eliminated, or you can say it's compensated. This way you can get very well focused beam. So as you see here, so by using the stigmator, so this is you can get a very nice image. This one with stigmation, no stigmation, is under focus, over focus. We have under focus or over focus. Electron we get elongated this direction or elongated along the other direction. We have the image like this. So generally, if you are very skillful, this term can be ignored. So in the end, the total beam size is given by the square root of dg. So this is what we want. So the size of the virtual source diameter divided by the magnification. For example, when we have 5 times magnification, the spot size on the wafer will be 5 times smaller than the size from the source. This one makes sense. This is the ideal case. Then we have this spherical aberration, chromatic aberration here, and we have the diffraction. From here you can see the higher energy, higher voltage, higher energy, we get smaller chromatic aberration and also smaller diffraction. This way you get higher resolution. But this is particularly true for the thermal ionic emission. For the thermal ionic emission SEM, normally we need high voltage to get very high resolution. But for the case of the field emission SEM, even at 2 keV, we can get easily 5 nanometer resolution. So you may ask, so why the formula is like this? Some people may think should be B equal to BG plus BS plus BC plus DD. Why not linear? Why we don't have this linear addition, but we have this square, then we have the square root. So this is because if you remember what you learned in the AE 343 for the case of the ion implantation, diffusion doping. So here we assume those aberrations, spherical chromatic diffraction, they are all Gaussian. They are those DS, DC, DD, these errors, they all have a Gaussian distribution, and they are independent from each other. They are random Gaussian. Then for the Gaussian distribution, you have the formula like this. So if we can draw this one in this curve. The first term is the source size DD is given by in this one. In this case, so the source size is virtual source is 20 nanometer. We have 5 times magnification. So we have 20 divided by 5. So this which is given by 4 nanometer. So this one, 4 nanometer is source size limit. So for the spherical aberration, it depends on alpha cubic. So this is the alpha angle here, beam conversion angle alpha cubic. The chromatic is alpha linear. The chromatic is linear dependent on alpha. For the diffraction, is the 1 over alpha is 1 over. So we have this diffraction. For example, so we have this 1 milli radius 0.001. 1 milli radius. This is the chromatic. So chromatic is given by 0.001 delta V over V and CC. So CC is given by 40 millimeter, delta V is 1.5 electron volt, and V is 30 kilo electron volt. In the end, you get this number here. You get easily get 2 nanometer. So the total beam is the sum. The total beam is given by this formula here is this one. Is given by this one. So then you may ask, what alpha is good? What alpha angle is good? This determines by the aperture size. Aperture size. Small aperture, you get small alpha. You get small alpha. This way you get smaller alpha. You get smaller beam size. But this you lose the beam current, because the beam current depends on, as we said, alpha square. So we have bigger alpha. You get higher current for the faster exposure. So normally for the case of the electron beam lithography, so the beam diameter is not the limiting factor for the high resolution. So the resolution, as we will see later on, is normally determined by the scattering of the electrons and also determined by the diffusion and the development process. So the beam size can be quite small. So here you can see the beam size is, you can get a few nanometers. But the resolution for the EV lithography normally is worse than 10 nanometers because of the development process. So as a result, you can use higher beam current, you still get good resolution. But we have higher beam current by using bigger alpha, you get smaller depth of focus. So if the wafer is not very smooth, this will be a problem. Here I want to say this part here, I need to clarify one thing. So here you have this alpha angle here, psi alpha. This alpha angle here, in principle, it should be this angle, right? So this alpha angle here should be this angle. But this alpha angle here is this angle. This one is similar to this angle. You can see the angle here and the angle here, they are not the same, right? So this angle here and this angle here. This is the really criteria. For the really criteria, we need these angles. They are not the same. But because they are proportional to each other, so bigger this angle here will give you bigger this angle. This you can see when it comes here, you get a bigger angle here. Because they are proportional, so roughly we say they are the same thing. Okay, thank you.